Okay, for 13, 14, and 15, they're asking you to look at graphs and then determine in 13 and 14 what the domain and range are of these graphs. Well, remember, domain are our x units. And as the x units go out in this direction, it goes from an interval notation, negative infinity to positive infinity. That would be interval notation, because they're going to go from left to right to our infinities. So, set builder notation, we say that x is such that x is all real numbers. And in set builder notation, it was like this. Interval notation is like that. And the range, again, goes down to negative infinity for the y's here. All the way up, it's the same. So it would be from negative infinity to positive infinity. And set builder notation, y now, is such that y is all real numbers. Okay, in number 14, you have a parabola. So, again, from left to right, it's going to go to eventually negative infinity to positive infinity, or set builder notation, x is such that x is all real numbers. But the range now, the range is starting here at negative 4. So you would write it in interval notation as bracket, negative 4 going to positive infinity. Now, how do you write it in set builder? Well, y is such that y is greater or equal to negative 4. That was what I was writing the other time, but this is the correct one here. All right, in this last one, and one of the things we would do is what is often referred to, let me put this in red. If you were to have a very, very thin line that you move from left to right over the graph, and you see as you move that line, does it intersect with the graph that you've drawn in more than one place? See, here it's just one place. And no matter where you put it, it's only going to intersect in one place. So we call this vertical line, as we pass it over the face of a graph, the vertical line test. And if it passes that, that is, it only intersects in one place, it is a function. So what do you think about number 15? And the answer is yes. It is a function. Now on the next page, I can do that one here because I remembered what it was. It's number 16. And the graph looks like this. Now does this graph pass the vertical line test? Well, again, it's going to intersect there and there. So it doesn't intersect in just one place. Here it's intersecting in two. So this is not a function. Now, 17 and 18 are often the kind of activity they want you to do with functions, where they will describe the function. They're going to say the function of x is such that negative 3x plus 1. And you might say, oh, look at that. That's like a slope-intercept form, which we said was y equals mx plus b. But remember, we can substitute the y for f of x. So if we're going to do this, then a t-chart is very appropriate. And during the class, when I give the lesson, I use this as well. So they're going to ask you for A, B, and C, 3 answers. And how do you find out what the output, that is the y value, would be? Well, you put the 3 in there. So negative 3 times 3 is a negative 9, plus 1 makes this a negative 8. If x is 0, then negative 3 times 0 is 0, and this becomes a 1. And then every once in a while they'll put a challenge in there. They want x to be a. Well, all you do is replace the x with the a. So this is going to become a negative 3. Now our x is a. And that's the answers. Okay, in example 18, and notice now they've changed the letter in the function notation, which is okay. It's still function notation. It's g of x now is equal to 2x squared minus 2. And you're just substituting. Remember, they're going to give you value for a is a negative 2, value for b is a 1/2, and value for c is 2 dot a. Well, 2 dot, that means 2 times. Okay? So let's do this one. So this is going to go into as x. Let me write it out here. 2 times a negative 2 squared minus 2. Well, a negative 2 squared is a positive 4. 4 times 2 is 8. Minus 2 is 6. Now, b is a little tricky. Let me do it for you. It's going to be 2 times, now x is 1/2 that we're going to square, minus 2. So 1/2 squared is 1/4 times 2 minus 2. Well, here, this then becomes 2 over 4 minus 2. But we can't do any subtraction there because this is not a fraction. So we have to make this a equivalent fraction of 4 over, let me put it this way here. This is going to be 8 over 4. There you go. So a negative 2 is equivalent to a negative 8 over 4. This simplifies to negative 2. So now we can do the subtraction. This is going to be 2 minus 8 is a negative 6 over 4. That when we simplify it becomes a negative 3/2. Let me be sure I'm getting that in. Yep. Now this next one's a little tricky. So we're going to substitute the a where the x is. And that gives us an a squared. And then we're going to multiply it by 2. So 2 times 2 is 4. And 2 times a negative 2 is a negative 4. So those are the answers. And again, lots of stuff going on here. On 19 and 20 are ones that are on the page that use a calculator, so graphic, we're not doing those. So for 21 though, it says here's a function of finding the surface area of a cube, and here's the formula. So they're saying if this is 7, what will y be? What will the area of this cube be? Well, we're going to put 6 times 7 that we're going to square, and it's going to be 6 times 49, and I believe that is 294 inches squared. So they're letting you move on into some higher algebra things as we go into function and then doing some substitution, but you need to understand the function notation here. Okay, as we do number 31, the previous page I deleted because there are just too many examples. And it said if f of x, where x is a 10/3, what would y be? Well, we're going to remember this is y equals a negative 3 times 10/3. There's our value of x plus 15. Now the 3's cancel out, and you're left here with a negative 10 plus 15. That equals 5, and that's where I get the 5 from. All right, this next is some general things, and again, I'm not sure how much we're going to include in the course, but it's here in this section. Some pretty heavy stuff here. It's asking you to find the domain where, in a sense, the equation is y equals x. Well, if you were to graph that, this is a line that looks like that. That goes through the origin there. And we did one like this. So in a sense, for x values, which is the domain, is x is such that x is a real number. That is, all real numbers are in the domain, because this would go all the way this way, all the way that way, and interval notation of this would be negative infinity to positive infinity. This one's a little tricky because they're wondering what value of x would make this denominator a 0. Take a look at it. If x were a negative 3, a negative 3 plus 3 would make this a 0. And therefore, x could not be a negative 3. Otherwise, this would be undefined. So when you're talking about the domain in which x is in the denominator, you're saying x is any real number, but x cannot be negative 3. So you are excluding from the domain of values of x that number that would make that denominator a 0. And that's how you write it. And this one, you might remember, is a parabola. We had that earlier. And for a parabola that opens up to the top or down, x is all real numbers. Interval notation, and it says x is such that x is all real numbers. Well, let's put x is any real number. All right. There are a few more examples. They're called piecewise functions, but we're not going to be doing them in our Math 100 course. So this kind of winds it up, and good luck, and again, watch it. Lots of good stuff here.